Yeah, but Omkar, who is the one is Sairam and that is getting a TA. Who else is there?
सर लाइव है सर आप.
Okay.
हेलो. हाँ सर, यू आर लाइव सर.
Yeah, fine. So, but there are how many participants? How many learners are there? Hello.
करंट वन आर वेटिंग सर, ओनली यू.
Only one learner is there.
यस सर.
So yeah. So yeah. Good evening. Can that learner talk to us directly, or you can put it in chat box? Hello, Omkar.
Hello, sir. The way it works is we are live streaming it on YouTube, and learner join only the YouTube stream. So it's a one-way communication for them. So they can they can communicate using YouTube's comment box, which your TA can monitor, and that's how it goes.
So
The
that
learners will not join this Zoom link. Learners will join only the YouTube streaming over there. Yeah.
okay. ठीक है. So good evening. Welcome to this live interaction session of the course. Electrical equipment and machines, finite element analysis. So I think 2 weeks have gone, and I think that means about 10 lectures would have been over, or more than that, I think. So if there are any questions on whatever videos have been seen by the learners, please put comments in the chat box. So in the first week, fundamentals of electromagnetics were covered with specific reference to finite element analysis, and that is video lectures from 1 to 10, from 11 to 20, the finite element method and procedural details are there. So if there are any questions by participants, they can put it in the chat box. So I have with me two TAs. One is Professor Sairam. He is from IIT Dharwad, faculty in electrical and electronics engineering at IIT Dharwad. So he did PhD at IIT Bombay some time back, and now he has joined as faculty there. And he had major role in this NPTEL MOOC course. And second TA is Dr. Grishma Mohan. She also was a PhD student here and had contributed significantly to this NPTEL MOOC course when it was first, streamed and first recorded and then streamed in 2020. And now she is a faculty at NIT Calicut, electrical department. So three of us are there, myself, Dr. Sairam and Dr. Grishma. So if there are any questions, please put it in chat box, and our TA, these two TAs can then help us know those questions, and we can answer them together. So Dr. Grishma, so you were saying that there were some questions already posted, right? So can we know those?
Hello, hello, sir.
Hello.
Sir, there are 2 questions
Yeah.
uh, in that sheet. sorry, only one question actually.
Hmm.
One student said there are no questions.
Hmm.
One learner told in 2D for E matrix, how do we decide the global edge number? Is there a sequence we should follow? Also, do we need to consider only boundary edges in E matrix or internal edges?
Yeah, so yeah, I will answer this, and Professor Sairam, you can correct me if I have not told the full thing.
Yes, sir.
So global ages, one can number in any sequence that doesn't matter. That is my first reaction to the first question. And second is internal edges are important if there are different materials, like for example, or different regions. For example, if you are modeling a transformer, core window in which two windings are there, LV and HV. So you want to define separate, parameters for both these parts, like windings, LV, HV. The material is, there are ampere turns there, so you will have to define ampere turn density if it is a magnetostatic problem. And so you need to define those internal edges also of the winding, so that those windings can be sort of distinguished by the core for giving specific inputs like ampere turn density and all that. So edges internal as well as outermost edges need to be defined. Boundary conditions have to be given on only outermost edges, and typically we give a equal to 0 on the outermost edges. As I think you must have noticed in one of the lectures, I must have told that value of A is not important. Anything you can give. Typically, we give magnetic vector potential A as 0 on the outermost boundary, but that is not a must because flux is calculated as difference between two magnetic vector potentials. So phi is equal to A1 minus A2 for two-dimensional case with 1 meter depth calculations. So phi is equal to A1 minus A2. So you can actually give any reference potential like 0, phi or 10. The values of flux density would not change. So, so Sairam, you want to add something?
Sir, that is fine. One thing that I would like to add is internal boundaries can be useful if we are giving some sort of potential boundary conditions, like in case of parallel plate capacitors.
Yeah, correct.
Yeah,
Yeah, so you want to define a bigger box in which there are capacitor plates, and there of course you have to give potential.
yeah,
Yeah, right.
and there
Whereas
is
in case of
yeah,
magnetic problems, typically you don't need to define potentials on internal edges, typically.
yes,
Whereas for magnetostatic problems or electrostatic problems, you may have to define. Like if you are placing a capacitor within a box, then outermost box, we have to give 0 potential, and that box should be far away from the capacitor, and then the capacitor plates have to be given whatever potential. So there, yes, internal boundaries also need to be defined with some potential. Yes, you are right. So Dr. Grishma, you have some comment to offer on this?
I think Grishma has not joined.
No, yeah, I can see Grishma
Ah,
Mohan. She's there. So Dr. Grishma, can you unmute yourself and say something if you want? Okay, while she is not able to
Sir,
unmute. Yeah. Okay.
sorry, I was muted actually.
Hmm. So
No
you have
comments
any
there.
comment on this clarification that we have given?
Yeah, it's fine, sir. No, I don't want to add anything more. That's fine.
Good.
Maybe if somebody wants, because they were asking mostly about eddy currents and all,
Hmm.
in most of our basically that response sheet. So if you
Yeah.
want,
So
we
okay. So on eddy currents, I think we replied on email that they can watch. lectures, video lectures 9 and 10, specifically 10, wherein the eddy current theory is explained. At the end of ninth lecture and then full 10th lecture, I think eddy currents are discussed, and the corresponding theories also well explained there. And some references are also given. I think there is uh, thing. And then there, of course, there is a one more in one more lecture later. We have discussed how to calculate eddy current loss in transformer windings. So that will be, I think, some video lecture between 25 and 30. I think I don't remember exactly the lecture number. So all that is there. And we have also discussed when you want to calculate eddy currents through finite element analysis, what care should be taken to define the mesh size and all that. Depending upon the excitation frequency, the skin depth gets decided, which is 1 over square root of pi f mu sigma. And if frequency is high, then the skin depth is smaller, and that's why your mesh size also becomes smaller. So that represents some challenges in terms of number of finite elements and all that. But yeah, there are ways and means to tackle those problems. And although not covered in this course, the researchers have found out some methods like surface impedance methods and all that to take care of this very small skin depth issue in finite element formulation. So after going through the ninth and tenth lecture as well as uh, you know the video lecture on calculation of eddy currents in transformer windings, if there are questions by learners, they can specifically ask through email, and those can be replied. Yeah. So any other question that we want to discuss?
Sir, there is one more question.
Hmm.
In Ansys Maxwell, there it a balloon boundary condition which does not force field equal to zero at the boundary and simulates infinite boundary. In such case, how are the necessary boundary conditions to solve the problem obtained?
So can you repeat the first part in ANSYS Maxwell? What is the
In
condition?
Ansys Maxwell, there is a balloon boundary condition
Which
which
boundary condition?
balloon boundary condition.
Value.
Balloon. Yeah, they call it as balloon.
Ah.
Balloon boundary condition which does not force the field equal to zero at the boundary and
So is it
simulates.
like in theoretical term, is it like an infinite boundary? Something.
Yes, it's like an infinite boundary and
Ah,
simulates an infinite boundary.
okay, okay. So yeah, so this infinite boundary, there in theoretical terms, it is called as infinite boundary, and it is discussed in some books on finite element, and that simulates a kind of decaying field in that infinite boundary. That means you mathematically it is basically inbuilt into the equations for that boundary, and it simulates or emulates a decaying field inside that thickness without really explicitly modeling finite elements in that thickness. So something similar, all these commercial softwares, they will call it by different names, and some, algorithms. There may be some differences, minor differences between algorithms used, but the key concept behind that is this.
And there is one follow continuation question. In such case, how are the necessary boundary conditions to solve the problem obtained? It is not clear actually what is.
Yeah, so there will be corresponding syntax in the commercial software. So as per that, one has to define. But if one has to code, then infinite. There are some books on finite element. They describe infinite elements. When I take this computational electromagnetic course in IIT Bombay, I actually have one lecture on infinite elements. So if this particular learner wants to know more about it, I can share that presentation with him, so he can write to us. Okay, so I think these two questions are taken care. So, Dr. Bishma, so we had some 4 5 questions now earlier. So, have we taken care all, or we can discuss something here?
So we have actually replied to all most of the questions.
Yeah. So, so now the course is at which 2 lectures? How many? 4 lectures are 4 weeks are over, right?
Yeah, sir, this is the fifth
So,
week.
so they would have completed up to 20 video lectures, right? Because it is
Yes.
totally 8 weeks course, no? Because
Yes,
September
sir.
end is
8 weeks. Yeah, we are already halfway cross.
yeah. So they would have completed about FEM procedure, completed almost like close to 20 lectures must have been over. I think. Okay, so I think are there any more questions? I don't see any chat box, so I think Sairam and Vishma, you may be able to see, huh? Chat box. Is it visible? So are there any new questions?
No, sir, as such. No, sir.
No, huh? Okay. So Omkar, can we then close this session because there are no further questions?
Yeah, sure, sir. I mean, it's up to you. I mean, if
Yeah.
there are any points you wish to discuss, you can, or you can close otherwise.
Yeah, so we can close because there are not many learners who have joined this. So I think maybe videos are self-explanatory and they are able to solve the assignment by themselves. So if they have any question, they are always free to write an email, and those emails can be replied. Okay, so with this, I think we close. Let us close this. Thank you.
तो स्टॉप करना है
Yeah, we can close the session. So shall I end?